Hi guys, thanks for tuning in. In this video I'm going to talk about vectors. You guys are probably familiar with the concept of a vector from, say, your physics class or previous calculus courses, but just as a quick refresher, a vector is a quantity that has both direction and magnitude. So fundamentally, a vector encodes more information than a scalar does, because a scalar has magnitude information without any direction information. And in a math class, we typically represent a vector in the plane as a directed line segment. So you'll often see figures that kind of look like what you see at the bottom of the screen here, representing vectors in a math class. What you want to realize, though, is these quantities are simply pointing in a direction, and the magnitude is the length of that line segment. But this is not geometry class. These aren't rays. These aren't lines. We're representing a vector using a directed line segment, but the vector itself is not actually a collection of points in the way that we think of a line segment being a collection of points. In terms of equality of vectors, we say that two vectors are equal if and only if they have the same magnitude and the same direction, but one thing that we don't require is starting that vector from the same position in space. One way to think about this is in a physics class, you often think about a vector in terms of a force, right? And so if you think of a vector as a force such as a gust of wind, it doesn't matter if you're standing in Chicago and there's a gust of wind coming from the southwest at 30 miles an hour, or whether you're standing in Sydney, Australia, and there's a gust of wind coming from the southwest at 30 miles an hour. If the direction and magnitude of that force is the same, you're going to experience that vector, you're going to experience that force in the exact same way. And so that's the way to think about it. Two vectors don't have to be at the same position in space to be equal to each other. They just need the same magnitude and direction. And this is kind of because a vector is not a line segment. For two line segments to be equal, we would want them to be in the same position in space as well, but a vector is not a line segment, it's not a ray, it's not a collection of points. Rather, we want to think of it in that idea, in that physics sort of framework where we think of it as a force or a push in some particular direction with some particular magnitude behind it. So with the diagram I just showed you guys, the only two vectors down here that are equal are v and y, because these are the only two vectors that have the same direction and magnitude. The length of these two directed line segments is the same, and they're pointing in the same direction. Every other vector is related in some interesting way, like w is the opposite of v and y, x is a scalar multiple of v or y, z has the same magnitude but it's pointing in a different direction, and then a is just unrelated. So in terms of describing a vector algebraically, I have three directed line segments on the plane in this diagram, and what's interesting is it turns out that all three of these are the same vector. They're the same exact vector, they just have a different starting point. But we have a little formula that we can use. We can get the algebraic representation of a vector by doing the tip minus the tail. You take the tip of the vector in the plane and the coordinates of the tail of the vector in the plane, and you subtract those two quantities, and that will give you your vector. And when you run through that process for any of these three vectors, you get the same exact vector. So the green one, the tip is at 4, 5. The tail is at 0, 0. When you subtract those component-wise, you get 4, 5. So that vector is 4, 5. It's more interesting for the blue one and for the red one. For the blue vector, we're at the point 3, 7 for the tip. The tail is at -1, 2. And when we subtract those vectors, we're going to subtract component-wise. 3 minus -1 is 4, and 7 minus 2 is 5. Look at that, 4, 5. It's going to be the same thing for the red one. The tip is at 6, 3, the tail is at 2, -2, and when you do component-wise subtraction on those two ordered pairs, you get the vector 4, 5. All three of those vectors are 4, 5. I can review vector addition and subtraction real quickly. Vector addition is just component-wise when you do it algebraically. So if I have the vector 4, 5 plus the vector 1, -3, That gives me the vector 5, comma 2. Again, component-wise addition. 4 plus 1 is 5. 5 plus negative 3 is 2. If we think of this geometrically, in the plane, we will start the vector v from the origin, and it's the vector 4, comma 5, so we go right 4 and up 5, and that's how we get to the tip of vector v there. And then from the tip of v, so right here, we're going to start our vector w. That vector is 1, comma negative 3. Now you could think of a vector as a change in x, comma a change in y, which means that I'm going to go right 1 and down 3 from that tip of v. So right 1 and down 3, and that'll give me the tip of w there. And now I just make a triangle. So starting from the tail of v, I'm going to connect to the tip of w, and that's v plus w, and look at that, it's 5, comma 2. I'm going right 5 units and up 2 units, and that's v plus w. So there's a geometric interpretation of vector addition, and there's an algebraic interpretation. From an algebraic perspective, adding ordered pairs is not that challenging. And also, it doesn't matter where in space this happens. So originally, I showed this to you starting from the origin. That's a matter of convenience. We could just as easily start vector v from a different point in space, follow the same set of rules, and we're going to get that same resultant. We're going to get the same vector addition coming out of that. We still get the vector 5, comma 2, right to the 5, right 5 units, up 2 units. W plus v, well, just like addition turns out to be commutative for real numbers, addition is going to be commutative for vectors as well. We don't really care the order that we add our vectors in. We're going to get the same resultant. W plus v is the vector 5, comma 2, just like the vector v plus w is 5, comma 2. Subtraction does care about the order in which it occurs, just like it is with real numbers. So we do component-wise subtraction here. If we want to do v minus w, 4 minus 1 is 3, and 5 minus negative 3 is 8. And if we want to see that in the plane, the idea would be to take the vector v, just like we did before, and then add the opposite of 1, negative 3. So there's the opposite of 1, negative 3. By the way, the opposite of 1, negative 3 is negative 1, comma positive 3. So left 1 unit and up 3 units. And that'll get us to negative w. And then v minus w is the same thing as v plus negative w. We just connect the origin to the tip of negative w, and there it is. And if you were to count that out, you would see that it's right by 3 units and up by 8 units, a change in x, comma, a change in y. And then w minus v does care about the order there. W minus v will be the opposite of v minus w, as you might expect. So there's w, there's the opposite of v, and then when we connect the dots, when we make our triangle, you could see that w minus v is negative 3, comma negative 8. It's the opposite of v minus w. Quick review of some other properties of vectors that you might have learned in the past. Dot products, that's going to be a component-wise operation here. So a dot product, it's also sometimes called the scalar product. And the reason that you sometimes hear it called the scalar product is we take two vectors and the result that we get is a scalar. So this is an operation that takes two vectors and produces a scalar quantity. We're going to learn a lot about dot products in this course, but for this slide, all you really need to know so far is that we're going to do component-wise multiplication, and then we're going to add up those results. So v1w1 plus v2w2, and this result is a scalar, hence the scalar product. You could do this in any number of dimensions. It's fine in 2 dimensions. It works with 3-dimensional vectors. In fact, if you guys ever go on and study like data science, what you're going to find out is there's a lot of problems in computer science that you can represent as 100-dimensional vectors or 1,000-dimensional vectors, whatever. And all of these vector operations that you're going to learn in this course will carry over to those other contexts. And so the things that you learn about 3-dimensional space, a lot of those intuitions you're going to be able to bring with you for a problem that's in quote-unquote 100-dimensional space, where each of those dimensions are one of the types of data that you're storing about whatever kind of problem you're trying to solve. So big data, a lot of that can be reduced down to problems about vectors that you're going to learn a lot about this year. In terms of the length of a vector, this notation here is not absolute value. That means the magnitude of vector v. And one way that you can compute the magnitude of a vector or the length of a vector is the square root of the dot product of the vector with itself. There's also a 3D distance formula. Hey, guess what? These are the same formula. They look a little bit different, but what we do is if we subtract p and q from each other, that's a vector connecting p and q. You can think of it as a tip and a tail. So if you think of p at the tip and q at the tail, then if you do p minus q, that's the vector connecting p and q. Same thing here. This p minus q, that's a vector. Oh, so really the distance between 2 points in Euclidean space is the magnitude of the vector connecting those 2 points. So the length of a vector formula and the distance formula really are the exact same thing. And then if you're curious about why this notation for magnitude of a vector kind of looks like absolute value, it's because they are related to each other. They're not the same formula. But this notation, the reason that we take it to be this distance formula is really what we're doing is we're thinking about having the point 0, 0 at the origin, and then we have our vector v, and our vector v is going to end at some coordinates here. Well, and you could call it v1 and v2, right, if you wanted to. The distance from the origin is the length of this vector. And so this what looks like absolute value bars, it's the distance from the origin to the tip of vector v. Just like when you guys were in grade school and you were learning about absolute values, when you're really young, you think of an absolute value as making a negative number positive, which, I mean, that is the net effect of taking an absolute value, but that's not really what's happening. What's actually happening when you're taking an absolute value is you're measuring the distance. Sometimes this ink pen likes to draw extra horizontal lines for some reason. Sorry about that. Anyway, when you're taking an absolute value, you're measuring the distance from the origin to the point on the number line that you care about. And in this case, that distance is 5 units. It's not that we made the number -5 into a positive. What it actually is that we're computing the distance from the origin on the number line to the number -5 on the number line, and that distance is 5 units. And it's no different when we go to a vector context. When we move up to vectors, we're still finding the distance between the origin and the tip of our vector. So that's why these notations do look very similar, but they're not exactly the same thing. And then this formula is going to come up a lot this year. It's really useful for finding angles between vectors. So this is an alternate way of finding a dot product between two vectors. It's the magnitude of your first vector times the magnitude of your second vector times the cosine of the angle between your two vectors. So please keep that formula in mind. There's lots of triad problems and lots of lit sheet problems that if you reduce it down to this formula, you're able to solve these problems pretty efficiently. So this is a very, very useful formula. It comes up all the time. I can give you a quick example. So we're going to find the angle between vector v and w right now. And now you could see, I mean, we can count it out, but vector v is 2, 5, and vector w is 5, -2. If you take the dot product between these two vectors, you get the number 0. Now, some of you guys might already know that if the dot product between two vectors is 0, then these two vectors are perpendicular. They meet at a 90-degree angle, but let's use that alternate dot product formula here. So what we can do is we could say, oh, okay, so we have a different formula for dot product right here. And we know that that dot product is 0 because we took it. So we're going to take that 0 that we calculated, and We're going to set that equal to the magnitude of v times the magnitude of w times the cosine of the angle in between those two vectors. Well, the magnitude of v is a non-zero number. The magnitude of w is a non-zero number. So the only way to satisfy this equation is for the cosine of theta to equal 0. And if we're going to talk about like small angles, the only small angle that we have that satisfies that is theta equals 90 degrees. Oh, well, if theta is equal to 90 degrees, the angle between v and w is 90 degrees. That is, v and w are perpendicular to each other. And that's just a general theorem. This will always work. If the dot product of two vectors is equal to 0, then v is perpendicular to w. And that's true as long as neither v nor w is a zero vector. Though even if v or w or both are the zero vector, it still kind of works, because you can think of the zero vector as a vector that's perpendicular to every other vector, because the zero vector has a dot product of 0 with everything. So it's kind of a special little mini vector that's perpendicular to all other vectors. But that's not really what we're concerned about here. The main way that we apply this theorem is we think of two non-zero vectors. If they have a dot product of 0, then those two vectors are perpendicular to each other. Okay, so here's something new that you didn't learn in your calculus class last year. I'm going to take two vectors, v and w. V is the vector 1, 5. W is the vector 6, 6. And I've got a new little definition here called projection, or in the course you guys are taking, you'll hear it called push all the time. So here's the formula. You do need to memorize this. So this is a very, very useful formula. At the beginning, this coefficient is a scalar. We're going to take v dot w and divide it by w dot w. That's going to be a scalar quantity. And we're going to multiply that scalar by the vector w. Now I'm going to crunch the numbers for you. So, nothing too exciting here. The dot product of v and w is 1 times 6 plus 5 times 6. W dot w is 6 times 6 plus 6 times 6. This entire thing is a scalar, and that scalar simplifies to the number 1/2. We're going to multiply that scalar by the vector 6, 6, the vector w. And 1/2 times 6, 6 is 3, 3. All right, so what the heck did we just do, right? Well, if we plot it, if you look at this graphically, it might make a little bit more sense. We have scaled w, in this case, down. We've scaled w down to a shorter vector, and it's the particular vector that you would need to form a little right triangle. You could call it the projection of v onto w, because it's a perpendicular projection here. What you can kind of imagine is maybe like the sun is shining in the sky, and you have rays of sunlight coming down perpendicular to w. And when those rays of sunlight hit v, what we're doing is we're kind of projecting v down in a way that makes a right triangle here. So that's what you can kind of imagine when you think of the term projection. This was what you might see in a more traditional math class. So if you might see this in an advanced statistics class in college, a linear algebra course. You would hear projection as the term for what's happening here, the projection of v onto w. In this net math course, it's a little bit more colloquial. When you read through the basics, it'll call it the push of v in the direction of w. And we can kind of look at this and say, is the push of v with or against w? And the way we interpret that is, you want to imagine that v is like a gust of wind or something, and w is maybe like the bearing of an airplane or something. Well, if this gust of wind, v, hits w as, it's a force that's representing the bearing for an airplane, what you want to imagine is this gust of wind, v, going to speed you up or slow you down as that airplane is flying through the sky? Well, you could see right here, the push of v in the direction of w is the component of v that's in the direction that w is already going. And we can see we get a little boost. Basically, v is not perfectly aligned with w, but if we take the component of v that's in the direction of w, we can see that it helps us on our journey. We get a little boost in that direction, a little extra force in the direction we're already traveling with. So we would say that the push of v is with the direction of w. And then I just mentioned this term, but this is also called the component of v in the direction of w. Guys, I'm going to stick with a very similar example. So I kept v the same. I changed w a little bit. Maybe this is like a smaller, slower airplane, but it's on the same course as the previous airplane on the previous slide. Let's run through the algebra again. V dot w over w dot w times w. This is the push of v in the direction of w. And when we crunch the numbers, something funny happens here. Our coefficient is a little bit different. We get 3/2. And our vector is a little bit different, 2, 2. But when we multiply it back out, we got 3, 3 again. If you look at it graphically, look at that. Remember the projection of v onto w in the sense that this is exactly how we'd have to rescale w to connect everything up to make a right triangle. So that's our idea of projection, to make a little right triangle there. It's kind of like the shadow that v casts onto w to make a little right triangle. But if we think of this as the push of v in the direction of w, again, if we're thinking like in a more physics sort of framework, we think of v as a force, or like a gust of wind or something. We think of w as a force, or maybe like an airplane that's hurtling through the sky. And this gust of wind, this force, hits the airplane, and we have to decide, is this glancing blow from a gust of wind going to speed us up as we're flying to our destination? Or is it going to be like having the wind in our face and it's slowing us down? And again, in this case, we could see that the push of v in the direction of w and w, both these arrows are pointing in the same direction. So we would say that the push of v is again with w. And another way of phrasing this, another term for this idea, is the component of v in the direction of w. Now, we're not always guaranteed that our force is going to give us a little boost. You guys, if you've ever ridden your bike, you've probably experienced this. If you've ever ridden your bike on a windy day where the wind is in your face, you've felt a force slowing you down. You're pedaling and pedaling and pedaling, and it feels like you're not going anywhere because the wind is blowing in your face. We could see an example of that as well, where the push of v is against the direction of w. So you could see maybe the common theme here. Each w that I'm picking is is along the same line, but they're different vectors every time. So w in this case has a different magnitude, and its direction is the opposite as before. So let's again use this formula, v dot w over w dot w times w. And when you crunch all the numbers, your coefficient ends up being -3. -3 times -1 is 3. -3 times -1 again is 3. Oh my gosh, we got the same exact vector again. Now the only reason this happened is that I picked all of my w's to be along the same line. So I kind of forced that to happen. That wouldn't normally happen with 3 random examples. But in this case, since w was not random, I was kind of tweaking it to illustrate different points. That's why that ended up happening. But look at this. The end result of this is, if you look at w versus the push of v in the direction of w, those two vectors are pointing in opposite directions. That is, we would say that the push of v in the direction of w is against w. We still get our projection, right? We still make a little right triangle, so v and the push of v in the direction of w can be joined together to make a beautiful little right triangle. But if we think about this from a physics perspective, what we're imagining is now we have a really slow airplane that's maybe flying home or something. Maybe this airplane is not in as good of shape as it was on its outbound journey, and now when it's flying home, it's kind of flying very slowly through space or something, very slowly through the air. And look at this, when the wind hits vector w, you could see it's kind of like having the wind in your face. It's slowing you down, and you could really see that by looking at the projection of v in the direction of w, or the push of v in the direction of w there. Guys, you'll get really good at that stuff as we do more examples, but always try to kind of keep that intuition about a vector being akin to a force, and the resultant of two vectors would be the net force after those two forces have both had a chance to act on each other. That's kind of a way to think about it. All right, so next, let's move on and let's talk about how to come up with the equation for a line parametrically. So let's just think old school for a second. Pretend you're back in junior high and you're learning how to find the equation for a line in good old y equals mx plus b form. And the most important thing to find would be this m, this slope, which, by the way, is a change in y over a change in x. So in this case, our slope is 5/4, as in our change in x is 4 units to the right, and our change in y is 5, and so our change in y over our change in x is 5/4. Well, if we want to do this in a vector sense, parametrically, we need a vector that connects the two given points. We need a vector that runs between 0, 0 and 4, 5. But you guys already learned how to do this earlier in the PowerPoint. We do tip minus tail, the tip being 4, 5, the tail being 0, 0, and 4, 5 minus 0, 0 is 4, 5. Oh, that's our vector that connects the 2 points that were given in this example. And there is a correspondence between slopes and vectors, by the way, because this vector is a change in x, comma, a change in y, while a slope is a change in y divided by a change in x. These are similar ideas. There are similarities between slopes and vectors that you want to keep in mind as we work through problems in this class, because I think knowing that correspondence will help you solve certain problems. Anyway, finally, the equation of our line, we're going to pick a starting point, and then we're going to move by multiples of this slope vector that we found. You can kind of think of this as a slope vector, in a sense. That vector is giving us a direction to move along as we generate more points on our line. So the equation of our line is going to be L of t equals a starting point. I'm going to pick 0, 0, plus multiples t of our slope vector 4, 5. And if we let t run from negative infinity to infinity, it's going to generate this entire line. So imagine yourself kind of starting at 0, 0, and you're adding on multiples of the vector 4, 5. And as that happens, as t runs from negative infinity to infinity, we're going to get our entire line from that. So kind of imagine a point starting at 0, 0 and moving along our line by multiples of the vector 4, 5. And when you let t go from negative infinity to infinity, that's going to generate everything. Now, if you just want to generate your line segment connecting these 2 points, you could restrict your domain for t, and you could say t just goes from 0 to 1. That will start you at 0, 0 and end you at 4, 5. But if you want the entire line, then you would want t to go from negative infinity to infinity. So for the line segment, similar idea. The slope of that line is, we're going to do tip minus tail when we do it in a vector format. But if we're just thinking old school, like stuff that we would have learned back in junior high, then we would have our delta x is 4, and our delta y is 5, and if we do delta y over delta x, we get 5/4. Oh, it's the same thing. So we do delta y over delta x, we get 5/4 there. The vector through those given points, you're going to do the tip minus the tail, so you have to find the coordinates of the 2 points on this line segment, but that doesn't take too long, right? It's just going to be 6, 3 and 2, -2. So if we do tip minus tail, 6, 3 minus 2, -2, we get the same vector, 4, 5. And the equation of this line segment, it's going to be L of t equals, by the way, when I say equation, I mean that we need an equal sign. it's not an equation unless there's an equal sign there. So this parameterization will be described using an equation. L of t is equal to, we're going to pick a starting point. I'm going to pick 2 comma negative 2 plus multiples of this slope vector 4 comma 5. Now, an interesting thing is that a line is not uniquely defined parametrically. What I mean by that is there was nothing special about the starting point 2 comma negative 2. There are infinitely many points on our line that we could have put there. 6 comma 3, for example. If we had L of t equals 6 comma 3 plus t times 4 comma 5, that would be the exact same line, the same collection of points in space. So the actual line as it's drawn out from that algebra is going to be equivalent even if you have a different starting point, as long as the 2 starting points are both on your line. So this parameterization I'm showing you guys does not uniquely define our line, but still it's interesting. And if we want to keep this a line segment, just connect the starting point and the ending point. Just restrict the range for t here and only let it go from 0 to 1, and that'll connect our endpoints. We'll connect the dots and nothing else. We'll start at the point 2 comma 2, and we'll move our way over to 6 comma 3, and we're good. We've traced out our line segment. Guys, in general, here's the formula that you're going to want to keep track of. It's L of t equals p plus q minus p times t. P is your starting point. Q minus p is a slope vector connecting our points p and q. And t is a parameter that, as we take multiples of our slope vector, as we let our parameter run over its range, that's going to generate all of the points on our line. So we have a starting point, we have a vector between the 2 points, and as we take our starting point plus multiples of that vector, it'll trace out that locus of points, that collection of points. And then you got to be careful, especially on a quiz or anything that's being graded. Always specify the correct range for your parameter, because you want to make it clear to your reader whether you are tracing out the entire line or just the line segment or whatever the case may be. By the way, this might be reminiscent of y equals mx plus b from your Algebra 1 course. If I write it in a slightly different order, y equals b plus mx, you can almost see a correspondence here, right? Like b is your starting point when you're thinking about an Algebra 1 problem. M is your slope, and how are you generating more points on your line? Well, you're taking multiples of your slope from that starting point, and that's going to trace out your whole line. This isn't that different. L of t equals p plus q minus p times t might look weird, but it's just a starting point plus multiples of a slope vector. So very, very similar to Algebra 1. What's really neat about doing these problems parametrically is we can extend these ideas to any number of dimensions. So you've never learned how to plot a line in 3-dimensional space before. Right now, it's really easy to do it now that we know how to do these things parametrically. So we find our vector, we subtract the tip minus tail. 606 minus 210 gives us 4, negative 1, 6. And that's going to be our slope vector. And the parametric equation follows the exact same format. A starting point plus multiples of a slope vector. And if you let t run from negative infinity to infinity, we're going to trace out that entire line. What's neat about this setup is you could do this in an arbitrary number of dimensions. So I can give you 2 15-dimensional points, and if I give you 2 15-dimensional points, you could come up with the equation of the line that connects those 2 points in 15-dimensional space as t goes from 0 to 1 for a line segment, or negative infinity to infinity for an entire line. Our brains are not capable of thinking about what 15-dimensional space would look like, but our theoretical background is strong enough that it doesn't matter that we can't picture it in our heads anymore. We could still do the algebra to parameterize that line, which is pretty powerful. By the way, guys, there are times where you might want to thread out your equation. So I do personally have a strong preference for writing the L of t equation. So I like this format. However, there are times that it's useful to say, you know what, I'm going to thread this out into an x of t, a y of t, and a z of t. For the x of t, I'm going to take 2 plus 4 times t. Oh, there's the 2 times 4 plus t. Or for my y of t right here, I'm going to take 1 plus t times negative 1, also known as 1 minus t. Notice how I'm just looking at this component by component, and that will take care of it. For our z of t, oh, that's not a great choice of color there because it's going to be very, very, very hard to read. Honestly, I'm just going to go back to yellow. I already used it once, but it works. So for my z of t, that's going to be my z coordinate of 0 plus t times this z coordinate of 6. Oh, 0 plus 6t. So if you ever want to thread out your L of t into 3 separate equations for 3-dimensional space, one equation for each of your coordinates, that's not too difficult to do. Now, if you were taking a more traditional calculus course, one thing that you would see fairly frequently is writing the xyz equation of your line. Once you've threaded this out, like we could see on the screen here, we could take our x of t equals 2 plus 4t, and if you wanted to, you could solve this equation for t. No big deal. So you could say, okay, this is x minus 2 over 4 is equal to t. I don't know why my pen keeps doing that. I apologize for the random horizontal lines that I keep getting there. I wish I could figure that out. Then you take your y of t equals 1 minus t, and you could rewrite that as t is equal to 1 minus y. And you could take your z of t and solve that one for t. And so if you have z of t is equal to 6t, that means that t is equal to z over 6. Oh, look at this. Let me switch to a highlighter here so I can show you what's going on. Look, t is equal to x minus 2 over 4, t is equal to 1 minus y, t is equal to z over 6. All 3 of these equations are equal to each other because they're all equal to t. So there is another way of describing this 3D line. You could describe it by 3 equations. That's messy. 3 equations with 3 variables to describe a line in 3-dimensional space. I'm not a huge fan of that, so if you can avoid doing that, that's great. And geometrically, by the way, graphically, there is a meaning behind having 3 equations like this for the xyz equation for a line. You would imagine the intersection between some planes, and the intersection between those planes would look like a line. I don't know if this is a great way to think about it. I think parametrically you get much better intuition. But I am showing you this xyz equation thing because, first of all, if you ever do see some materials from some more traditional calculus courses, you'll see this idea. And then also I think there's a try it problem where you're supposed to find the xyz equation for a line once just to show that you can do it. So this way you've seen it. All right, let's talk about parallel and perpendicular lines when we're plotting parametrically. So what we're going to do in this problem is we're going to find the equation of a line parallel to the one shown in this picture, but our parallel line is going to start at the point 2, 5. So our parallel line is going to start at this point. Well, the basic setup is very, very similar to what you knew in junior high. If we could find the slope of the line, and if we have a starting point, that's enough to find the equation for the line. So if we could find the slope of the line we want to be parallel to, I think we're good. So I'm not going to explain this too much because I think you guys probably get the idea here, but the slope of this line, we want to find a vector connecting these 2 points. So I went right by 1, so delta x was 1, and then here delta y was 2. Oh, so the vector between my 2 given points was 1, 2. You can also just subtract the ending point from the starting point. That'll also give you 1, 2. And then you guys know how to find the equation of this line. It's a starting point plus multiples of a slope vector. L of t is equal to 3, 1 plus t times 1, 2. That's the equation of our line. Now, I'm trying to find the equation of a line parallel to this one, so I just have to make a slight adjustment. If I start at the point 2 comma 5, but retain that same slope, I think I'm all set. So same slope, that's the property that two parallel lines have, is that they share a slope. And then the equation of my line is 2 comma 5 plus t times 1 comma 2. And there it is on the screen. That's a line parallel to that green line is parallel to the red line. The only difference is that it passes through the point 2 comma 5. Perpendicularity, we could really take advantage of dot products and how dot products, if you take the dot product of two vectors, when the dot product is 0, those two vectors are perpendicular, we can use that to kind of force some perpendicular lines. So in this problem, I'm keeping the same line, but now I want to find the equation of the line that's perpendicular to the given line that passes through the point 3 comma 1. So basically, I want my perpendicular line to go through the point that I just circled. Okay, so the steps here are pretty straightforward, though. Find the slope vector for the given line, which is the same line as before, so it's still 1 comma 2. The equation for the line is the same as it was before. But to find the perpendicular line, look at this. If the slope of the red line is 1 comma 2, then if we want these two lines to be perpendicular to each other, I need these to have a dot product of 0. Well, you can kind of do this in your head. If you do 2 comma negative 1, that'll do the trick. If you swap the x and y coordinates and make the second one negative, or not negative, but it's opposite, that'll take care of it, because this dot product would be 2 minus 2, which we know is 0. So at least in two-dimensional space, it's really easy to find a vector that's perpendicular to another vector. You just swap the x and y coordinates and make that y coordinate its opposite. It actually doesn't matter which one you pick, but here, let me show you. I can do this algebraically. So if you look at this from an algebraic perspective, we could think of our first slope as a change in x, comma, a change in y. Now we want to force perpendicularity here. So if we make our second vector a change in y, comma, the opposite of that change in x, that'll be 0, 0. Now this minus sign could have gone by the delta y instead. You'll still get 0, 0, or, oh, I said 0, 0, I apologize for that, 0. It's a scalar product, right? So when you take the dot product of two vectors, you get a scalar. So that dot product is 0. Sorry about that. But anyway, the point is, when you take that dot product and you get 0, that tells you that your two vectors are perpendicular. So 1 comma 2 dotted with 2 comma negative 1 is 0. Likewise, that general formula gives you 0. So you can always find a vector perpendicular to another vector in two-dimensional space without doing a lot of work. And then finally, the equation for our line is, we know the starting point, 3 comma 1, because it was given to us. And then the slope, we just found the slope vector. So we're good. We have the equation for that perpendicular line. And we are guaranteed that there's a 90-degree angle between those two lines. Again, guys, we can thread that out as two equations just for practice. I'm not doing this for any important reason here, but we have our 3 and we have our 2t. So that's our x of t. For our y of t, we have 1 and then t times negative 1, so 1 minus t right there. And I've threaded those out, that L of t out into two separate equations. There are times that that's really useful to be able to do. All right, so general summary here, I'm going to go through this super fast. In two-dimensional space, we can always define a line parametrically as a starting point plus multiples of some slope vector. If we're talking about parallel lines, same slope, but different starting point such that that starting point is not on our previous line. So one caveat with parallel lines is you need to make sure that they're distinct from each other, kind of like train tracks here where there's no overlap. So you do need to make sure that your starting point for your parallel line is not sitting on your other line, because if they share a point in common, they share all their points in common, in which case you don't have parallel lines, you actually have the same line twice. So you want to be careful with that. By the way, this symbol right down there means not in case you haven't seen that before. So this symbol means in. If you put a slash through it, not in. And then the equation of a line perpendicular, you swap the values in your slope vector and make the second term its opposite, and that'll do the trick. That's not the only way to do it, but that's certainly a fast way to remember, and we know that it works because the dot product of a comma b and b comma negative a is equal to 0. If we want to talk about doing all of this in three-dimensional space, no big deal. Same formulas here. The only thing we have to be careful about is, and even parallel lines are the same thing. We don't really have to be careful with parallel lines. 2D and 3D are going to behave the same for parallel lines. You just want to make sure that whatever point you have for your parallel line is not on your previous line. And then just use the same slope for both of them. And you got a pair of parallel lines. Perpendicularity is more interesting because when we're talking perpendicularity, we aren't able to just kind of swap the A and the B and make something opposite. So I can only give you a more general technique, which would be, we know that two lines are perpendicular to each other. Perpendicularity is tougher in 3D. We know that these two lines are perpendicular if v dot w is equal to 0. So that's the only way to determine it. If we're talking about three-dimensional space, we just need a vector w that has a dot product of 0 with v. And then guys, I think that this is probably a good place to wrap it up because we're at 45 minutes here. But I'm going to do a second part to this video that I'll post online tomorrow for you. So what we'll pick up with tomorrow is if I give you two pairs of lines, can we determine if these pairs of lines are perpendicular to each other? And I'll show you some techniques for figuring that out. All right, guys, I hope you enjoyed this video. Tune in for part 2 that I'll be posting tomorrow.